Okay. Yeah. So so this is the last class before the midterm week. Okay. So yeah, in the light of some requests to for regarding the midterms and the increased workload, I extended the deadline for the assignment 2. Okay. So it's now the next Sunday. Okay. So it's 21st. Okay. So I hope that will help you guys. Just joining.
Our exams end on next Sunday, 21st. So it's
Okay, so that doesn't help.
not really, but thank you for explaining it.
Okay, so one thing is, if yeah, of course, many of these need programming and all that, but it of course will help you if you at least try some of these questions beforehand. Even in your midterm exams, that is going to help you. Okay, so yeah, so you just try and see if you can finish it by next week. I hope since this was posted like quite some time back, I hope this should be possible. Otherwise, if you really want, we can extend it for some more time. Okay, so don't get stressed out. Okay. All right.
Thank you,
Ma'am,
ma'am.
what will be the syllabus for midterm?
Yeah, so the syllabus will be whatever is done till today, including today's class. Okay.
But there's no holiday before this exam. I mean, on 19th we have ML exam and it is 4 to 6, and after that Saturday 10 to 12. So
Yeah, so the idea is you have a lot of time like before already, right? So, so today you're going to learn something and you have a week away, right? The exam is on next Saturday only.
but there
So,
are so many subjects.
yeah, I understand. So I will try to, give more weightage to the portions done beforehand than today's class. But you might end up requiring something from today's class also. So, okay, so I want you to be like, when you come back after the midterms, I want you to be up to date on the syllabus. So that's the whole idea. But yeah, I get your concern. So I'll try to keep that in mind while setting the exam paper. Okay. Right. Okay. So yeah, any questions, any concerns till now? I hope the questions have been like quite clear to all of you. Okay.
Yes, ma'am.
Okay. So, okay, so let's just resume from where we were doing the previous class. So, we were looking at linear programs, and in particular, we were looking at what are called these basic solutions. Is my screen shared? No, right? Yeah, okay. So I think now it should be fine. The screen's visible, right?
Yes, ma'am.
Okay, so we were looking at linear programs and we were looking at these basic solutions. Okay, so in particular, the thing that we were trying to utilize is what we know about a system of linear equations. So that is the feasible region of the LP. And we in particular looked at, we talked of the standard form of linear programs. Okay, so something of this where, all these, the system of equations, you represent it using equalities. Okay, and the inequalities are only for the non-negative constraints on X. Okay, so these are the only kind of inequalities that will show up in the standard form. Okay, so the reason for this was, to utilize what you know about the system AX equals B to build on it and try to solve this optimization problem. Okay, so yeah, so that was the kind of intuition or the motivations for looking at this form, and we also looked at these ways to convert it into this form. Okay, so again, I would like to iterate that this way of trying to convert it into this form, it's just one of the ways. Okay, in the sense that getting something in this form, the standard form, and then trying to solve it, it's one of the ways. Okay, so you will see that this kind of methodology of what we're trying to do is deeply connected with what is called the simplex method, okay, for solving linear programs. So that's why you have these very specific ways of putting slab variables and surplus variables and all these free variables and all that. Okay, and also the notion of basic solutions, where you say that you can divide the columns of the matrix A into two groups, right? And so that one set of columns is linearly independent. It's an M cross M submatrix. Okay, and so one possible solution is to set all these other variables corresponding to the other set N as 0. Okay, and then try to find the unique solution to the system Bxb equals B. Okay, so try to find the Xb which fetches you this value. Okay, and yeah, so this kind of a solution is what we called as the basic solution, right? And while doing this, it could be that some of these Xb's were also negative. Okay, so so that can happen in a basic solution. Now, in addition, if you have a basic solution where all these Xb's are greater than or equal to 0, such a solution is going to be fully feasible for the system Ax equals B and X greater than or equal to 0. So then you call it a basic feasible solution. Okay. So now we saw this notion of degenerate solutions. So I just want to iterate that, I just want to mention that in these degenerate solutions, you could have even basic solutions themselves which are degenerate, and also basic feasible solutions which are degenerate. So the only thing is, when we say it's a degenerate solution, what we mean is that even in these Xb's, some of them can become 0. Okay, it's not that only the Xn's are 0. Some components of Xb also might end up becoming 0. And that's when you have a degenerate solution. So you can have the same thing even for a basic feasible solution with some of the Xb's 0. So it is still feasible, right? So that's a degenerate BFS. Okay. So we saw some examples of writing basic feasible solutions, right, and basic solutions, the distinction between the two. And then we were looking at this fundamental theorem of linear programming. It said that if a linear program has a feasible solution, then it also has a basic feasible solution. And if it has an optimal feasible solution, it also has an optimal basic feasible solution. Okay, so the reason for why this theorem is important is that it reduces the search space. Instead of searching the space of uncountable solutions, you can restrict your attention on these basic feasible solutions, and that is a finite number. Okay, so because why is it finite? Do you have thoughts on why it's finite? Guys, am I speaking to myself?
Only like some of the XR and XPs will be non-zero, so that we can make combinations of how many X's and XPs are at any time non-zero. So that will be a finite number.
Exactly. So it boils down to choosing the particular columns. So if you have n columns, it boils down to choosing which m of them you want to choose as the basis, and so making the rest of them as 0. So the number of such solutions is finite. Okay, it can be a large number, but it's still finite. Okay.
Ma'am?
Yes.
Ma'am, our variables are in the R real, like that is that might be in Rm. Even if we reduce it to m dimensions, then even then the solution will be in Rm.
The solution is in Rn. So this is a matrix. The matrix is of size m cross n, right? So the number of x's, there are n of them.
Yes, ma'am. Yes, ma'am. Yeah, even if it is Rn, so the point was that how are these solutions finite?
Oh, no. So overall, the number of solutions is still uncountable, okay? It's not a finite set. But the thing is that because of this fundamental theorem, which lets you look at these basic feasible solutions, that number is a finite number, right? Because it boils down to how you choose the basis, right? So once you fix a basis, then the XB, right, selected in this manner, this is unique because B is the columns are linearly independent. Okay, so for each B you fix, there is one corresponding solution, right? Xn's are all 0 anyway. So this is the solution corresponding to each B. Now, you can vary the B's, right? There are different ways of choosing the basis. So we saw an example here, like where we chose these two, the last two columns. Okay, so that was one way. The other way is choosing these two columns maybe, and maybe even this. Okay, so there are different ways of choosing the basis. So it boils down to, choosing m of these columns, right? So m is less than n here. Okay, so out of these n columns, in how many ways can you choose m columns? Okay, and of course these m have to be linearly independent, but at max the number of ways is n choose m. That's it, right? So okay, so that's why the search space is quite reduced. Okay, in this manner. Okay, so then we were so that's what we said, and we were trying to prove this. So while proving it, we showed the first part. So if there is a feasible solution to an LP, then there is a basic feasible solution. Okay, so to see that, what we did is we started from a feasible solution. Okay, and then what we said is, we were trying to analyze how many of the values Xi's are greater than 0. Okay, so in any feasible solution you take, so because it's feasible, you have this condition. These have to be satisfied, right? If A1 to AN are the columns of A, you have this linear combination should give you B, and all these X's should be greater than or equal to 0. So now you try to see the ones which are strictly greater than 0. Okay, so the idea is you're trying to say that, if many of the X's are equal to 0, perhaps that would be the non-basic variables. Okay, the intuition is of that kind. Okay, so suppose exactly P of them are greater than 0. Okay, and so then you're trying to see whether these P, so the columns corresponding to these P, so A1 to AP, so those are sufficient to express B. And if these are already linearly independent, then this X itself is a basic feasible solution. Okay, but now the case is if these P's are, if those are not linearly independent, so if those are greater than M, okay, so then for sure they are not going to be linearly independent. So then what do you do? Okay, so one point in this aspect, like if these A1 to APs are linearly independent, then we're done. So an additional point I wanted to just say is, it could be that these P's are less than M also. I mean, it may not exactly be that you have M of them, but if say it's a system like where M is 5. Okay, so there are 5 equations, and here you have only, say, some 3 linearly independent columns. Okay, so then it means that the other 2 X's are 0. Okay, but still that is fine. It is a degenerate solution, but it's still a basic feasible solution. Okay, now in the other side is when these columns were not linearly independent, we tried to construct another solution, which was a basic feasible solution. So the idea was to use these these multipliers. It's to basically eliminate one of these columns. Okay, so you have A1 to AP. So somehow try to eliminate one of these columns and still express B. Okay, so that's when we had this expression, right? X minus epsilon times these Y's. Okay, so that's the one we used, and we had a particular way of choosing these epsilons. This epsilon, so that all these terms are greater than 0. okay, are greater than or equal to 0. They can end up becoming equal to 0 also. That's fine. Okay, because by the same idea, then you'll have degenerate solutions maybe. Okay, you may have like more than some of them becoming 0. Okay, so you want at least one of them to become 0. Okay, so that's when we ended up with this x minus epsilon y, and this contained p minus 1 positive variables. So this x tilde, which was exactly x minus epsilon y, contained p minus 1 positive variables. Okay, and so the overall flow is this, right? We started off with an x where p of the variables had a greater than 0 value, and the n minus p of them took a value 0. And since this p was greater than m, what we try to do is we construct a new x tilde with p minus 1 variables, taking a positive value, and the rest of them as 0. Okay, so basically this was the new value, and you can keep doing this till you get the case where you can express it in terms of these exactly m solutions, m or less than m. Okay. So that was the first part of the fundamental theorem. So now I hope this proof idea was clear. Okay, so I kind of rushed through it towards the end of the last class. I couldn't logically conclude it. Okay, so I hope this was clear, right? Were there any questions on the first part of the proof?
No, ma'am.
Ma'am, I just wanted to clear out one thing, that our rows are considered independent here, right? All the equations.
Yes, yes, yes. Okay. So because the rank of the system is m, okay, so there are m linearly independent rows.
Okay.
Okay. Yeah. Any other questions? Okay. So
I think the rows will always be linearly independent, because the slack variables or the surplus variables which get added, they sort of like an identity matrix thing and towards the right side of the rows.
No, so what we initially started off with is the rank of the system is m. So it's exactly m of the rows. I mean, so the rows are always redundant. I mean, of course, if you add the slack variables, of course, that's there. But even without that, the assumption is this: you're having this system has a rank m. So there are m of them, which are anyway linearly independent, right?
Yes, ma'am.
So Rohit, was that okay? Was there
yes.
any other? Okay. Okay. So so if that is clear, so now let's move to the next part of the proof. It says that if the LP has an optimal feasible solution, then there is an optimal basic feasible solution. Okay, so the difference just comes with respect to this optimal word. Okay, so so the idea is kind of similar to this first part itself. Just you need to take care of the optimality parts. Okay, so so let's just see that. So suppose you're given an optimal feasible solution. Okay, so the x's are optimal and they're feasible. Okay, so because they're optimal, then what you have is C transpose X is going to be less than or equal to C transpose Z for all other Z which are feasible. Okay, so because of the optimality. Okay, now so the same idea, right? So from this you're trying to construct a basic feasible solution which is also optimal. Okay, so suppose again by the same way, like there are p positive variables, so the x1 to xp's. So these are the positive valued variables. Okay, and now if these are again linearly independent, now already this x itself is a basic feasible solution, and it's also optimal. You're given that it's optimal, so we are done. Okay, so now so because of that, let's look at the other case, right? When these A1 to APs, they are not linearly independent. Okay, so there is, I mean, some dependencies between these columns. So then we know that, if you take any B, so since these are linearly dependent, there are multiple ways to express any b, right? So because by the very nature of these p positive variables, we have that a1 x1 plus a2 x2 plus so on plus ap xp. This is 0. Okay, but now because they're dependent, there is at least one more solution like this, right? A1 y1 plus a so on up to ap yp is equal to b. Okay, and where these x's and y's are different. So this follows as a consequence of the linear dependence, right? Because a solution to ax equals b is not going to be unique. Okay, so you have multiple solutions here. Okay, so then you can make use of these, right? So you can again, by the same idea, you can construct this x minus epsilon y. Okay, and that's going to have p minus 1 positive variables like earlier. Okay, but is that going to be still optimal? That's the point. Okay, so maybe I should, I think in this part we are looking at this as 0 itself, right? So yeah, because we are looking at x minus epsilon y, so this is 0 itself. So just forget what I said about these giving you b. In both of these giving you b, so that's not the idea. So let me just retrace a little bit. So there are p positive variables, and these a1 to aps are dependent. Okay, so that means you can find a combination of them which gives you 0. And we know that a1 x1 plus a2 x2 plus so on up to ap xp is equal to b. Okay, so you have this just like the earlier step. Okay, now again, like what we did in the previous part, we can compute this x minus epsilon for some suitably chosen epsilon. Okay, and this is going to have some p minus 1 positive variables, and it's feasible. But the question is it going to be optimal? Okay, so the claim is that yes, it's going to be optimal, something constructed this way, because we are going to show that this quantity C transpose Y, this is going to be 0. Okay, so because this C transpose Y, if it becomes 0, then when you take this new point C transpose X minus epsilon Y, the second term C transpose Y is 0, so this doesn't make a difference. So you're going to get back C transpose X, and here we have a new solution X minus epsilon Y, which gives the same objective as the optimal. So this is also an optimal BFS. So that's the idea of the proof, but we still have to fill in why this is 0. Okay, so let us see that. Okay, yeah, so the thing is, it's a very natural notion. So suppose you have C transpose Y as less than 0. So if C transpose Y is not equal to 0, there are two cases. So C transpose Y less than 0 or C transpose Y is greater than 0. Okay, so then if C transpose Y is less than 0, so you can construct this point X plus epsilon Y. Okay, so, okay, for some value of epsilon, or perhaps the same value of epsilon, okay, such that all these entries are greater than or equal to 0. Okay, and if you take C transpose X plus epsilon Y here, this is going to give you C transpose X plus epsilon C transpose Y, and this is going to be less than 0, right? So this here you have something which is even better than the optimal. Okay, so that cannot be the case, right? Because we assume that X was an optimal solution. Okay, now by the same logic, even if you have C transpose Y is greater than 0, okay, similarly you can take instead X minus epsilon Y. Okay, and here you have to be careful about what epsilon you choose. But like in what we did earlier, you can set it so that all these X minus epsilon Y's are greater than 0. Okay, and so then what you're going to get is this is going to be a better point than X. Okay, so both these cases cannot occur, and that's why you need C transpose Y equal to 0. Okay, so yeah, so that's the whole idea. So are there questions at this point? Is this proof clear, or anything, any steps which are unclear?
Clear, ma'am.
Clear, okay. What about the others? Viransh?
Ma'am, could you just once again repeat what was C supposed to be? I think I missed it.
Okay, C was the objective of the LP, right? So the standard form LP had this form. So min C transpose X,
Okay,
AX
okay.
equals B.
Okay. Yeah. Thank you.
Yeah. So with respect to optimality, it's you need to. So when you say the X is optimal, it means that C transpose X is less than or equal to C transpose Z for every other feasible solution. Okay. Because this is the objective we are trying to minimize. Yeah, somebody typed. To share it's clear. Okay. What about the others? Viransh, is it clear?
Yes, ma'am. Yes, ma'am.
Okay. What about the others?
Just to clarify this, the second part of the proof means that any set of linearly independent vectors that are in the basic feasible solution, they are the optimal solutions. Any
It's not any X is. I mean, you will have some things in the some basic feasible solutions which are not optimal also. Okay, but the point is there is some basic feasible solution which is also optimal. It's not the case that every basic feasible solution is optimal. Okay, that's not the idea. Okay.
Understood.
Okay.
That was like the assumption that we were making, that the X we are taking here is the optimal one. I missed that.
Yes. The X, we are starting with an optimal feasible solution, and then we are constructing another basic feasible solution for which the objective C transpose X minus epsilon Y. Okay, so that is going to give you the same value as C transpose X. Okay.
Yes, ma'am.
Right. What about the others? I want to hear from you guys. Is it clear? And what about Devansh? So you can type in the chat box if if you're not comfortable to speak.
I need to review a little because I'm have difficulty to set it up completely. So I'll have to review everything and start.
Okay. So do you want me to explain any particular point?
No, ma'am. I also need to clarify what particular point I'm missing at. So I'll review it completely once and look at it.
Okay. Fine.
And ma'am, a small request. Can we do an example question of this type if possible, like where the constraints are given of less than or greater than, and you have to find one of the x's, or we have to find the x's?
You want to find the x's as in the optimal feasible. Okay, so what we are going to do later is to devise a method to compute this optimal feasible solution, right? So at this point, what I've told you is it's a theory. So it says that, if there's a feasible solution, there is an optimal basic feasible solution and all that. But I've not told you how you can compute this optimal BFS.
Oh, okay. Then it's fine. Then it's fine.
Right.
Because I thought we have to figure out the method from this proof itself. And
No. Oh, no. So the method itself, so that is what is the simplex method. Okay, so I felt that, the reason for why simplex method would make sense would be this fundamental theorem of LPs. So that's why I thought it's better to, look at this aspect first before going into the simplex method. Okay.
Yes.
But yeah, we will come to examples of, how you'll compute these optimal set and all that. Okay.
Yes. Thank you.
Right. So yeah, I just want to ask others, what about Siddharth Solanki? So Siddharth, Shah, Nidish, it's clear for them, good. Siddharth Solanki, is it all right?
Ma'am, how do we choose the epsilons exactly?
Yeah, so the epsilons, if you remember, so in the what we had was this x minus epsilon y in the hope of trying to eliminate some of these variables. That's the whole idea behind, trying to move from a feasible to a basic feasible solution. right? You're trying to eliminate some of these dependencies on some of these columns. Okay, so in the process, we are constructing this new point, x minus epsilon y. Now you also want to have these values to be greater than or equal to 0. You want all these to be greater than or equal to 0. Okay, that holds even for the next point about these moving from an optimal solution to an optimal BFS. Okay, so if you're trying to do that, so you want to ensure this is true. And so that's why we have a very particular way in which you can fix this epsilon. So the way is, you try to find this minimum value of these xi's by yi's. Okay, so ultimately you want all these to be greater than 0. So if you set epsilon as the minimum value of these xi's by yi's, and in particular where all the yi's, out of all the yi's which are greater than 0, so then, so suppose this is going to be met at some k. So at the minimum value of this xi by yi, so you'll compute x1 by x2, x1 by y1, then you'll compute x2 by y2, and so on. Okay, so up to xp by yp. Okay, so all these you're going to compute, and out of these there's one thing which gives you the min, so call that k. So xk by yk, this is the one which gets the minimum out of all these. Okay, so this minimum value, you fix that as epsilon. Okay, and that is actually equal to this xk by yk. Okay, so now if you take this xk, so if you compute this xi minus epsilon yi for all, so let's maybe just do that. Okay, so if you take xi minus epsilon is what? Xk by k. So let's take I is 1. Okay, so let's take x1 minus xk by yk times y1. Okay, so that's what this is, right? Xi minus epsilon y1. So I'm 0 or less than 0 or equal to 0. What do you think?
Yes, ma'am, got it.
Got it, right? Because this is greater than 0, because xk by yk is less than or equal to x1 by y1, right? It's true for in general, xk by yk is going to be less than x2 by y2 and so on. So this value is going to be greater than or equal to 0, to be more precise. Okay, so in that manner, the same thing will hold for every other xi's, so x tilde i's. Okay, so that's the reason why this epsilon is fixed in this manner. Okay, so similarly, even for the other cases, like for the second part of this proof, that's the way how you will fix the epsilon, so that you want to ensure that all the variables are greater than or equal to 0. Okay, so I hope that's clear. So in particular, that will be especially in this case, right? X minus epsilon y. So when we said that X is an optimal BFS, and then we are trying, X is an optimal feasible solution, and we are trying to construct an optimal BFS. Okay, so then we said that the same methods you could use, and then you come to this X minus epsilon y. So then this epsilon, this choice of epsilon is crucial here. When you say that C transpose y, if you assume this is going to be greater than 0, so then X minus epsilon y, this particular way of setting the epsilon will make this feasible. But at the same time, it will make X minus epsilon y a better point in terms of the objective, right? So that's why this cannot occur. Okay, so yeah. I hope that clarifies things a little bit.
Yes, ma'am.
Okay. Okay. What about the other students? Rajneesh. Are there any questions, Rajneesh?
Ma'am, actually, I was not able to hear you. It was a network problem from my side.
Okay. So yeah, I hope you guys will go through the videos and just revise these concepts. Okay, so now so this is the fundamental theorem. Okay, so now let's just try to get some more intuition on these basic feasible solutions, right? So we saw an algebraic method. So this is of choosing different ways of choosing the basis. Now, geometrically, let's look at what it means. So for this, I want to talk to you about extreme points. Okay, so if you take any convex set C, a point X is said to be an extreme point, if you cannot express this in terms of a convex combination of other points. Okay, so so in short, you can't have a representation like this, that X is some alpha 1 times x1 plus 1 minus alpha times x2, okay, where alpha lies between 0 and 1, okay, strictly between 0 and 1. So to give an example of this, if you take this this as your set, as your feasible set, so everything within this triangle, okay, so if you take some point inside, okay, so this is not an extreme point, okay, because you can represent it as a convex combination of, say, these 2 points. I mean, there are also other ways you can represent. You can represent it as convex combination of these 2 points. Okay, so it lies on a line joining some other 2 points, and you can represent it that way. Okay, but now if you take some points here, basically the vertices. Okay, so let us just take this one. So this vertex, let's take. Okay, so is it possible to write this as a convex combination of any 2 points in this set? Is it possible to find 2 points, the convex combination of which gives you this?
No.
No, right? So yeah, if you take some point here, you will need something else here to represent it as a convex combination, and this goes outside, right? Similarly, any point you take, you will not be able to find the other point. Okay, so that's the same thing with all these sort of corner points. Okay, so these are what we refer to as the extreme points. Okay, so this is some notion you can define for any convex set. Okay, so suppose you take this as your convex set, so everything inside, right, and including the boundary. So what are the extreme points?
There are no extreme points.
There are no extreme points?
Okay, yeah, then all the entire perimeter is the...
Yeah, exactly. So everything on the boundary, you cannot write it as a convex combination, right, of any 2 points.
Ma'am?
Yes?
But then how is this a set, a convex set, because we cannot represent one point as the convex combination of any 2 points inside the set?
No. So convex set just means that, I mean, it's not that you have to represent every point as a convex combination of the other 2. That's not the thing. So if you take any 2 points and you draw a line joining the 2, that point will be in the set. It's not the other way that, that you should be able to represent everything as, okay?
Yes,
yeah, good point. That's a good point, actually. Okay. Yeah. So in convex hulls, this thing comes up about representing. Okay. But anyway, by the Degenerate theorem, that tells you that you have a limit on that number. Okay. So that could also be 1. You can, I mean, in that sense, you cannot represent it using more than 1 point. That's also it comes in the Degenerate theorem as well. Okay, so I hope this notion of these extreme points is clear. Okay,
Yes,
so it's just intuitively the corner points, or if it's a polytope, you have the vertices of the polytope. Okay, so the key thing here is that these BFS, these basic feasible solutions, actually correspond to the extreme points. Okay, so basically these two, the set of extreme points is exactly the set of basic feasible solutions to a linear program. Okay, so here we are talking specifically about the linear program. Okay, because it's basic feasible solutions, it's we are defining it for a linear program, right? So this is for a linear program. Okay, so so let's again try to see why this is true. Okay, so we need to show both ways. So if you have a basic feasible solution, show that it is an extreme point, and if it is an extreme point, show that it's exactly a basic feasible solution. Okay, so let's start with this. Suppose you have a basic feasible solution. Okay, and so you want to now show that it's an extreme point, which means that you cannot represent it as a convex combination of two other points in the set. Okay, so this is a basic feasible solution, and so in particular there are these x1 to xn's and the rest of them are zeros. Okay, and it's feasible, so that's where you have this, and also all the xi's are greater than or equal to 0. Okay, and yeah, so suppose this is not an extreme point, so that means you can find two other points y and z, such that a convex combination of these y's and z's will give you x. Okay, and in particular these y's and z's have to be feasible. Okay, so that's where you have this as true. Okay, so note that since in in x, all these last few components are 0. Okay, so remember the convex combination. There is a convex combination, say alpha y plus 1 minus alpha z, which gives you x. Okay, so because of that, even and all these alphas are between 0 and 1 strictly. Okay, and you also have that all these y's and z's are greater than 0. Okay, so that means even the last few entries, the entries m plus 1 to n of y's and z's, those also have to be 0. Okay, otherwise you can't have this the convex combination of them giving you 0, right? So so that's why you only consider the first m components of these vectors. Okay, so now this itself gives you a contradiction, right? Because these a1 to am, those are linearly independent, because x is a BFS, and because it was a BFS, these a1s to ams were linearly independent. Okay, so then the way to represent them, to represent any b using these a1s to am, there's a unique way. Okay, but here we are telling you that there are two ways to write this, and that cannot happen. Okay, so that's why this assumption is wrong. So you cannot have this kind of a representation, and that's why x has to be an extreme point. Okay, you cannot have two ways to write this. Okay, so I hope this side is clear. Okay, now on the other front, suppose you have an extreme point. Okay, so what we showed now is if you have a BFS, it's also an extreme point. Now, if you have an extreme point, so is it a BFS? So that's what we have to show. Okay, so it's an extreme point. That means there are no ways of writing it as a convex combination of two other points. Okay, so in particular, let us say that these x1 to xk, these k values are non-zero, and xk plus 1 up to so on up to xn, these are 0. Okay, so the claim is that these a1 to ak's, these are linearly independent. Okay, so again, if this is not the case, then you can find some combination, not all y's are 0, not all y is 0, such that this is true. Okay, if these are not linearly independent, so then this will give you two solutions like this, some x minus epsilon y and x plus epsilon y. So if you take these, these will also be feasible, right? And if you take this epsilon, like similarly like what we did earlier, if we adjust the epsilon to be very small enough, these values will be greater than or equal to 0. And these 2 points, if you take, the convex combination will give you x. So that will contradict the notion that x is an extreme point. Okay, so that's why, it's an extreme point, and so these columns have to be linearly independent. Okay, and so that claims that of course this has to be less than or equal to m. The k has to be less than or equal to m the moment they become linearly independent. Okay, so that shows that this is indeed an it's a BFS. Okay, so I don't know if this idea is clear to you all, whether it made sense.
Yes,
Yeah, it's clear. Okay. Okay, so please stop me if something is unclear. Okay, so I just wanted to, take some examples and illustrate these ideas. We've been seeing a lot of, like jargons and some, ways of mathematically manipulating things. So let's just see, some pictures of these. So let me consider this system, x1 plus x2 less than or equal to 1, and these are greater than or equal to 0. So to convert it into the standard form, what do? So this, you
Slack
just
variable.
add slack variables, right? So x1 plus x2 plus x3 equal to 1, and x1 greater than or equal to 0, x2 greater than 0, x3 greater than 0. Okay, so this is the system. Okay, so let's just try to first draw this system, what it means. Okay, so this is x1 and this is x2. So x1 plus x2 less than or equal to 1 would be, let's just draw x1 plus x2 equal to 1. Okay, so that would be something like this, right? Okay, this is a line. Okay, so when x1 is 0, you have x2 is 1. And when x2 is 0, you have x1 is 1. So it's this line here and basically this part of the line, right? And you have x1 greater than 0 and greater than or equal to 0 and x2 greater than or equal to 0. So this is the feasible region. Okay. So now if you look at the extreme points of this region, so what you're going to get, what are the extreme points? So it's basically these corner points, right?
0, 0.
Yeah, 0, 1, 1, 0, and 0, 0, right?
Yes,
okay, so this is the set. So now let's compute the basic feasible solutions. So the basic solutions, let's compute here. So how do we do that? So this is just the system. It's just a single equation and 3 unknowns. Okay, so the basis should be of size 1. So you need to fix a 1. So the B should be an R1 cross 1, right? So one of these columns you fix. So these are like, okay, let me just write this. So this is the A. Okay, A is this.
That number of equations is 1. Then what?
And three variables are there, right? So M is 1 here and N is 3. Okay, so you need to choose a submatrix of size 1 cross 1, right? So it's just going to be a single scalar number in some sense, right? For this example, okay. So basically one of these columns you have to choose. So let's just pick this. So by definition, this is going to be, so the basis is just this this entry. Okay, so this will correspond to, so remember this, this corresponds to x1, this corresponds to x2, and this corresponds to x3. Okay, so I'm fixing this basis as this element. So my basic variable is x1. So x1 is a basic variable. And x2 and x3 are both zeros. Okay, so basically this part of it is n. And that I'm fixing those as non-basic variables. So that means the x2 and x3 are both 0. Okay, so this will in short give you x1 is 1. Okay, so so remember this x3 is an additional thing that we added to this original feasible system. So this basic feasible solution is this. And here it corresponds to 1, 0, right? x1 is 1 and x2 is 0. So it corresponds to this. This vertex or this extreme point. Okay. Now, if you fix alternatively, if you fix say this one, so if I fix this as the basic variable, okay, so that means x2 is the basic variable, x2 is basic, and x1 and x3 are 0. Okay, because this, I hope this is clear. So the system, you would write it like this, right? And so this column corresponds to x1, this to x2, and this to x3. Okay, so if I fix this part as basic and these two columns, and I'm going to use that to represent the n. Okay, so that would mean that x1 and x3 are 0 and x2, because it has to satisfy this, so x2 is 1. Okay, so that would give you, so basically this, right? x1 equals 0, x3 is 0, x2 is 1. So basically this point. This basic feasible solution corresponds to this extreme point. And similarly, you can verify that if you take x3 as the basic variable, you're going to get this as the extreme point. Okay, I'll leave that for you to try it out. So was this clear, like how we did this computation? Any questions on this part? Okay, am I audible?
Yes, ma'am.
Okay, are there any confusions on this, like how we computed the extreme points?
I missed the entire solution. I had to get the door. I'll watch
Okay.
the video. I'm sorry.
Okay, no worries. So yeah, maybe I can just go over another example. Like I have about 5 minutes if I'm already late, but maybe just to get this idea across. So if you need to go somewhere, have some other work, please feel free to do so. These will be recorded anyway. So let's just take another system, right? x1 plus x2 less than or equal to 1, and 2x1 plus 3x2 equal to 1. Okay, so here this is an equality and this is an inequality. Okay, so if I draw the system, what am I going to have? So this is x1 and you have x2. So again, x1 plus x2 equal to 1 is going to give you this. Okay, and this side, right? Okay, and x1 greater than or equal to 0, x2 greater than 0. So basically this, the first quadrant. And now 2x1 plus 3x2 equal to 1. So what are, how does it look like? So when x1 is
half
0.
Comma 0, half comma 0 to 0 comma 1 by 3.
Okay, so half comma 0. So this is this point, and 1/3 comma 0, right? So you set x1 equals 0, you get x2 is 1/3, and you set x2 equals 0, you get x1 is half. So something like this. Okay, so this is the system, and this is an equality condition. So basically everything on this line. Okay, and you also have this side. So the feasible region with respect to these inequalities is this part, which is shaded. And you have these greater than or equal to 0 for both x1 and x2. And on this line. So basically what the feasible region is just this line segment, this part. Okay. I hope this is clear.
Yes, ma'am.
Right. So now, so the extreme points are just these two. Right. So what was it again? So you have half 0 and 0 1/3. 1/3, right? So these are the extreme points. Okay. So now let's look at the basic feasible solutions. So for that, what we would do is you add these slack variables, x3 equals 1, and you have 2x1 plus 3x2 equal to 1. Okay. So here the matrix corresponding to this is 1, 2, 1, 3, and 0, 1. Right?
1,
so, 0. Sorry, 1, 0. Thanks.
And I'm really sorry, but could you explain that thing again? In the previous example, you said that something about the basis dimension, and so these are two equations, so something like that.
Yeah. So let me just explain with respect to this example, maybe. Okay. So here there are 2 equations and 3 unknowns, right? And so this is the matrix A. Okay. So out of this, you want an m cross n system. So that was the set of basic column vectors, right? The basis. So you need to pick 2 of these. Okay. So because there are 2 equations, so this A is m, okay, R2 cross 3. So you need to pick 2 linear independent columns at each time to get the basic feasible solutions. Okay, so let's take maybe let's take these two as the basic part. So this is the B, and let's fix this as N. Okay, so this corresponds to what? X1. Sorry, I shouldn't write it this way. So this is X1, X2, X3. Okay. So first column is X corresponds to X1, this corresponds to X2, and this corresponds to X3. Okay, so when we fix this as N, so it means that we say X1 is 0. Okay, so the first column corresponds to X1, so that's non-basic, so X1 is 0. Now for computing the basic variables, so what you have is X2 plus X3 is 1, and 3X2 equals 1. Okay, so you need to solve these two systems. So this is going to give you a unique solution. So the solution is what?
1 by 3 and 2 by 3.
X2 is 1 by 3 and X3 is 2 by 3. Okay, so overall you have X1 is 0, X2 is 1 by 3 and X3 is 2 by 3. So that corresponds to this solution, right? 0, 1 by 3. Okay. So that is one basic feasible solution. So now let us fix maybe these two, like this one. So let's write it again. 1, 1, 1, 2, 3, 0. So let me fix this as my B.
This will give half 0.
Yeah. So this would mean what? X2 is 0. Right, and the same way you follow the same thing, so you'll get X1 plus X3 is 1 and 2X2 is 1. Sorry, 2X1 is 1. Okay, so this will give X1 is half and X3 is again half. Okay, and X2 is 0. So that is going to give you this solution, half 0. So this one, half 0. Okay, so now there's one more basic solution you can get, right? So we looked at using these two as the basis, and we looked at using the first and third as the basis. So let's look at the first and the second as basis, right? So 1, 1, 1, 2, 3, 0. So now this is the basis. And so this one, X3 is 0. So basically you need to solve these two systems. X1 plus X2 is 1 and 2X1 plus 3X2 is 1. Okay. So what do you get when you solve this? Okay, are you all still here? Okay.
X2 is 1. No.
X2 is 1, is it? So let's just try this. So 2X1 plus 3X2 is 1. So now you can multiply the first one with 2. Right, so and then you just subtract these two. So what you'll get is X2 is minus 1.
Minus.
Right, and and X1 is
2,
right? Yeah, so this is
not possible.
Yeah, so this is, so where does this lie? So this is X1 is 2 and minus 1, right? So this is actually this point, right, where these two lines meet. So this is a basic solution, but it's not feasible.
Yes, ma'am.
Okay, so yeah, so this is actually, this is not even an extreme point as well. So the extreme points are just two of them, and those correspond to the basic feasible solutions. Okay, so yeah, I just wanted to bring this idea that these basic feasible solutions are nothing but the vertices of the convex region that we consider in linear programs. Okay.
So to find the optimum, we have to compare, like check if the objective function is minimized for which of these 2 points.
Yeah, exactly. So that's the whole idea. So you just compute all the vertices and find which one is optimal. So that is one way. Now, in many, in some systems, like, even this number of extreme points, number of vertices can also be large. So instead of, computing all the vertices and then, going through all of them to find the best, you can do something little smarter in the sense of, you start from some vertex and try to go towards a vertex which will improve your solution. Okay, so that is what the simplex method is all about. Okay, so but yeah, in principle, yes, if you have a few vertices, you can just enumerate all the vertices and compute the best solution there.
Yes, ma'am.
Yeah. Okay, so yeah, I think I will stop here. I mean, I just wanted to reach a logical point before the midterms. Okay, so yeah, feel free to reach out if you have any doubts or anything. Okay, so good luck with the exams, right? And I will meet you all next week on Saturday morning. Okay.
How will
Right.
So during the exam, we have to open this video.
Yes, you have to keep your video enabled. And there's, yeah, strictly no collaboration. So it's an open book exam. So you can refer your notes, your textbooks, and you can refer online, but you cannot collaborate among yourselves. Okay.
Yes, ma'am.
So, right. Okay. All right. So thanks, everyone. I'll hang back if you have any questions. So otherwise, all the best.
Thank you, ma'am.